in the last part of the video, what we have obtained that the impedance of a string is can be given as Z is equal to T by C. Okay, but we also know that for a transverse wave, for the transverse wave when it travels through the string, the relation between tension and the velocity can be given as T is equal to rho into C square, that we have already obtained. So what we are going to do, basically replace the value of T, which is equal to rho C square. So C rho into C square. Okay, so the Z is equal to what we obtain, Z is equal to rho into C. Okay, now you see the velocity of the transverse wave in the string, it is determined by the elasticity of the string and the inertia of the string, elasticity of the string and inertia of the string. Okay, now Z is also a parameter which depends on C. Therefore, we can also say that the elasticity of the string and the inertia of the string, these two factors is responsible for the impedance Z which the transverse wave obtain when it travels through the string. Okay, so if the string has mass per unit length value higher, then the impedance to the traveling wave will be more, as you can imagine, and if the velocity of the string is velocity of the transverse wave is higher, then also the impedance will be more. Therefore, Z is equal to rho into C. This is the characteristics parameter for the impedance of a string. So this parameter we will going to use it when we discuss about the reflection and transmission of waves through the string. Okay, so with this, let's discuss the a new topic, which is basically the reflection and transmission of wave, transverse wave in the string. Okay, now so far what we have considered, that one end of the string is, suppose this is a string, one end is fixed and we are going to apply some oscillating force. Suppose we are just vibrate the string like this, and other end of the string is totally free. Okay, we have not put anything on the other end of the string. Okay, now what happens, what if we just struck the one end of the string with some oscillating force, and other end we just we just keep fix the other end, or maybe the other end we hold with by our hand very tightly. Okay, suppose in this end we also fixed it, or we hold the other end of the string. Okay, then what will happen, we are basically going to discuss that phenomenon. Okay, so once you plug the once you hit the string at this end with some oscillating force, the wave will travel like this, the wave will travel through the string like that. Okay, now since the other end of the string is now very tightly held, therefore the wave cannot pass through this part, because the other end is fixed now. So what may happen, the wave which is which reach at the end, it may get reflected back to this direction again. So it may change the position, and it will it may change its direction, and it will travel in the opposite direction. This wave we call as a reflected wave. Okay, I mean when you say that you are holding the other end of the string very tightly, that means you are providing an impedance where Z is equal to infinity, but I mean very high impedance you are providing, so that the wave cannot no longer passes through that other end of the string. Therefore what it will do, it will just reflect back. I mean it's the same with the light reflection. When the light found an obstacle, then either it transmit or it may reflect back. Okay, so in this way the string wave will, the transverse wave will reflect it if we put z is equal to infinity at that point. Okay, now you know that the string itself provide a impedance z is equal to rho c, but it is not enough to reflect back the wave by itself. If we hold the other end of the string tightly, then z is equal to infinity, and the string will the wave will reflect back from the other end of the string. Okay, and what if you hold the string not that tightly, so that one part of the string is still free? Okay, in that case what will happen, that some part of the wave will transmit through this part. Okay, one part will be reflect and another part will be transmitted through this loose end of the string. Suppose I mean, say little part of string is not when you held the other end of the string, one part of the string just gets free. Therefore, if the string find a medium to propagate, if the wave find a medium to propagate, then it will travel through the remaining part of the string. Okay, so in that case, that wave will name as a transmitted wave. Transmitted wave. So there will be three kind of wave. The initial wave will be our incident wave. Incident wave, and if it gets reflected, then it's a reflected wave, and if it passes through the string, to the other end of the string, then that wave is known as the transmitted wave. Okay, now we are going to write the equation for the incident, reflected and transmitted wave. So first consider the incident wave. Incident wave. So incident wave equation, we have written it many times, and it is like suppose a1 is the amplitude, a1 e to the power I omega t minus k1 into x. Okay, so this is the equation for incident wave. Okay, now what will be the reflected wave? Reflected wave. Reflected wave is thus the wave moving in the opposite direction, but its amplitude should be different from the incident wave, because a part of the energy will be lost during diffraction. Okay, so the amplitude would be different, as we can expect. So in this case, the wave equation will be, say we are now the amplitude is b1, so this will be basically b1 e to the power I omega t, but now it's moving towards the negative x direction, so it will be e to the power I omega t plus k1 into x. Okay, wave number will be same, because I mean, after all, it is in the same boundary. Okay, so if suppose this point is x is equal to L, and this is equal to x is equal to 0, so the incident wave and reflected wave are all basically confined in this part, so the wave number will be same. Okay, and also the frequency of the wave, it will be also same. So the equation of the reflected wave is basically b1 e to the power I omega t plus k1 into x. Okay, now third, the third will be the transmitted wave. So what will be the equation for a transmitted wave? Transmitted wave. So transmitted wave, basically it travels in the x direction. Okay, but since you see now k is the wave vector, k is equal to twice pi divided by lambda. Okay, we are assuming that there is no change in wavelength during the reflection or the incident, during the reflection and transmission of the wave. Okay, there will be no change of the frequency. Okay, if frequency doesn't change, then the value of the k, because k is equal to twice pi over lambda, lambda depends on frequency. Okay, so k should not be changed, the magnitude of k should not change. But mind you, when you write k into x, k dot x, basically k and x both are vector quantities. Okay, but as the transmitted wave, it's traveling in a different direction, therefore what happens is that although the magnitude of k remains same, but its direction may differ. Okay, so for a transmitted wave, we are going to use a different wave number k2. For incident and reflected wave, similar kind of wave numbers are used, because we know that in the reflection or transmission, the wave frequency, that's why the magnitude of k does not change, and during reflection and incident, only things matter is that one is traveling in x direction, other is traveling in opposite x direction. So we have used the similar value of k for both incident as well as reflected wave. But incident wave, it may travel in other direction also. Incident and reflection direction was parallel to x, but in this case the transmitted wave may make an angle with the x-axis. Okay, so therefore for the transmitted wave we are going to use a different wave number, although we are going to use the same frequency. Okay, different wave number means it basically represents the direction. The magnitude will be same, because the frequency, that's why the wavelength of the wave is same. Okay, so transmitted wave, what we can write, say a2, okay, e to the power I omega t. It is also in the positive k direction, so we can write e to the power I omega t into k2 into x. Okay, so this is the three equation for and this is three actually mathematical expression for incident wave, reflected wave, and transmitted wave. Okay, now what we are going to do, we are going to basically find out the relation between the coefficient a1, a2, and b1 using some boundary condition. Okay, so we are basically going to use some boundary condition and find out what are the relation between this coefficient a1, b1, and a2. Okay, from that what we will determine, we will going to find out the value of the reflection and this transmission coefficient. Okay, okay, so suppose the wave is this is x is equal to L point, where we hit the string with a oscillatory force. So and this is x is equal to 0, x is equal to 0. So this is the incident wave. Okay, and say this is the transmitted wave, which is traveling in the opposite direction. Incident wave is traveling in this direction, and suppose some part of the wave is being transmitted. So this is the transmitted wave. Okay, so at the point x is equal to 0, we are going to apply the boundary condition. Okay, at the point x is equal to 0, what we are going to do, we are going to apply the boundary condition. Okay, now at x is equal to 0, what we can write is the incident wave, if the displacement for incident wave is written as yi plus reflected wave, that must be equal to transmitted wave, because incident wave minus a reflected wave, it will give the transmitted wave. Okay, and we are putting it as a plus sign because we have already taken in the negative x direction in the equation. Okay, so at x is equal to 0, we can write yi plus yr is equal to yt. So displacement of incident wave displacement plus reflection wave displacement, that will be equal to yt. It's as simple as that. But I mean, yt should exist as a summation between y and yi and yr. Okay, so what we can write, a1 e to the power I omega t minus k1 into x plus a2 e to the power I omega t plus k1 into x is equal to b1 sorry, this was b1, sorry, this part was b1 is equal to a2 e to the power I omega t minus k2 into x. Okay, at x is equal to 0. So basically what we are going to do, we are going to put x is equal to 0 in this expression. So what we will get, a1 e to the power I omega t plus b1 e to the power I omega t is equal to a2 e to the power I omega t. Okay, so this part, these are same, therefore we can write a1 plus b1 is equal to a2. Okay, so and amplitude a1 plus b1 is equal to a2. So this is our equation 1. Okay, so next equation will be equal to the next boundary condition will be is that at x is equal to 0, at x is equal to 0, the transverse force should be also equal. Transverse force should be equal. Should be equal. Okay, if you remember what was transverse force, suppose I have already discussed it. Suppose this is at x equal to 0, we are considering an element, then t sine theta, this component should be equal to I mean f1 f naught e to the power I omega t. This condition I have already discussed, and in this case t sine theta will be our transverse force, because t sine theta will balance by this force. This was the transverse force, therefore t sine theta was our transverse force, and its value was minus because the direction is opposite. And t sine theta we have written as t del y by del x, right? T del y by del x at x is equal to 0 in that earlier case, in the last part of the video. Okay, now what we are going to do, we are going to put the same condition at x is equal to 0 here. Okay, so if we equate the transverse force at the both side, because at this point the transverse force, there should be one value of the transverse force. So for a reflection and incident wave, what was the value of the transverse force? That should be equal to the transmitted wave. So this is very simple expression. Okay, so what we can write, if we equate the transverse force in both directions, then t into del by del x, in this case y will be our incident plus reflected wave. Okay, so minus the del by del x, yi plus yr should be equal to minus the del by del x into yt. Okay, so tt basically get cancel out, so del by del x yi plus yr is equal to del by del x yt. Okay, so now we have to differentiate. This is at always at x is equal to 0. Okay, x is equal to 0, that you have to remember, at x is equal to 0. Okay, so now we have to differentiate with respect to x. Okay, so if we differentiate this expression with respect to x, what we will get, minus k1 into a1, okay, e to the power I omega t minus k1 into x. Okay, as very simple, plus plus then this also, now this will be plus k1, so that value will be equal to k1 into b1 e to the power I omega t plus k1 into x. Okay, it will be equal to, and this value will be equal to minus k2, right? So minus k2 into a2 e to the power I omega t minus k2 into x. Okay, so if we differentiate and equate both sides, then what you will get, minus k1 a1 e to the power I omega 2 k1x plus k1 b1 e to the power I omega t plus k1 x is equal to minus k2 a2 e to the power I omega t minus k2 into x. Okay, now the x value is 0 here, so this term and this term will not exist, because k into 0 will give us 0, and also there will be e to the power I omega t everywhere, so basically we can cancel this term also, e to the power I omega t, this term we can cancel. Okay, so finally what we will get, finally what we will get, minus k1 into a1 plus k2 into b1 is equal to, sorry, minus k1 a1 plus k1 into b1 is equal to k2 into k2. Okay, at x is equal to 0. Okay, so now what we are going to do, we are going to we are going to rearrange this expression a little bit. For example, what we can do, we can multiply it by t at both sides. So t is nothing but the tension. So K1 B1 into T is equal to K2 A2 into T. Okay, just little bit of rearrangement, nothing else. Okay, but we know what is the value of K1. K1 will be basically omega divided by C1. Okay, A1 into T plus K1 omega divided by C1 B1 into T, and K2 will be equal to omega divided by C2 A2 into T. Okay, because you see this was the incident part, and this was the reflection part, and this was the transmitted part, right? So the transmitted part velocity will be different from the incident and the reflected part, because we have different assume a different value of K2. K2 is a vector quantity, so it's if its direction is different also, then K2 will different from K1. Therefore, corresponding to that, this wave velocity will be different. In this part, the incident and reflected wave, they have a wave velocity C1, but in this part, the wave velocity should be C2, because K2 is different in this part of the medium, that I have already explained. So we can write minus omega divided by C1 A1t plus omega divided by C B1t is equal to omega divided by C2 A2 into T. Okay, so now what we can do, we can rearrange it again. T divided by C1 plus into A1 plus omega T divided by C2 into B1 is equal to omega T divided by C2 into omega into A2. Okay, there is a special motivation in order to write the expression as T by C1 and T by C2, because we know that T by C1 is nothing but rho into C1. Okay, T by C1, this factor, if you remember, what was it? It was nothing but the T by C1, rho C1 is nothing but the impedance of the medium, impedance of this part of this part of the medium between x is equal to 0 to x is equal to L. Okay, so impedance of the string, let me say the impedance of the fixed in of the string, and the Lozin of the string, the impedance is T divided by C2, and its value we can write rho into C2. Impedance of the same string, but it's the loose part which just exists beyond x equal to 0. Okay, so this is the impedance of the loose part of the string, Okay, so T divided by, in place of T divided by C1, we can write rho into C1, and which is nothing but Z1, and T divided by C2, the impedance of the string, which we can write it as Z2. Okay, so therefore we can write minus omega Z1 into A1 plus omega Z2 into B1 is equal to omega Z2, sorry, this is Z1, Z2 into A2. Okay, so omega get cancel out everywhere, so what we will find, Z1, if we take it common, B1 minus A1, okay, will be equal to Z2 A2. Okay, so okay, I made a mistake here. There was a minus sign here, because these two things are almost equal in structure. So this is minus, this is minus thing, so this will be minus, so this will be also minus, and this will be minus. Okay, so if we multiply it minus, then Z1 will be equal to A1 minus B1 is equal to Z2 into A2. Okay, so this is our equation 2. Okay, what was our equation 1? Our equation 1 was A1 plus B1 is equal to A2. This was our equation 1. And what is our equation 2? Equation 2 is basically this part. Z1 into A1 minus B1 is equal to Z2 into A2. Okay, so from here we are going to find the ratio between B1 by A1 and then A2 by B2. Okay, so next step, what is our aim? In order to find the ratio between A1 by B1 and A2 by A1. Okay, now you see what is B1? B1 is the amplitude of the reflected wave and A1 is the amplitude of the incident wave. So this ratio basically will give us nothing but the reflection coefficient. Okay, reflection coefficient is a quantitative measure how much incident wave is reflected. Okay, so incident wave is A1 and how much it will reflected, it is given by the ratio B1 by A1. Okay, similarly, as you could have imagined, A2 by A1, it's given the transmission coefficient. Because incident wave is A1 and a part of A2 will be transmitted. Therefore, the ratio A2 by A1 basically going to give us what is the transmission coefficient. Okay, so in the next part, I am going to use these two expression A1 plus B1 is equal to A2 and this equation 2, and we are going to find out the value of the reflection as well as the transmission coefficient. Okay, so this is a very important derivation, and you have to, I hope you are able to follow it. Okay, so next part I am going to find out these two coefficients, reflection as well as transmission.